37.
Number 37. So I didn't record that earlier. I start recording right now. So this is integral of x squared minus 3x plus 7 over. This is from 7.4. Yeah, this is from 7.4. Let me write it down here. So 7.4 problems. And the denominator, we have x squared minus 4x plus 6 being squared dx. Wow, okay. I wonder if there's any way for me to play tricky stuff here. So partial fraction decomposition. The denominator, I will complete the square at once. No, I do it later. So x squared minus 4x. That's definitely not factorable, right? Okay, that's not factorable. So we will have x squared minus 4x plus 6, ax plus b, and then x squared minus 4x plus 6 squared. This is cx plus d multiplied by
This is
the
where
LCD.
I wasn't sure. I wasn't sure what. I mean, it seems so simple, but I was like, I didn't know this looked okay.
The thing is, like, this is not reducible, and this is squared, so I need to do it twice, right?
Right.
Okay, and the numerator will be 1 degree less. So if I multiply by the LCD, I will get, so ax plus b times x squared minus 4x plus 6 plus cx plus d. Nothing to make it right. You know what? I will just do grouping. So ax cubed, and then how about the x squared? X squared will be negative 4a plus b. For x, that will be 6a minus 4b. And the constant, 6b plus cx plus d. Okay, I go on further. Ax cubed plus negative 4a plus b, x squared plus 6a minus 4b plus c times x plus 6b plus d. Now from here we see the x cubed term is 0 on the left hand side. So the a is also 0. Okay, and then x squared term, the left hand side, the coefficient is 1, the right hand side is negative 4a plus b. Negative 4a plus b, but a is 0, so b equals to 1. Now for x term, the coefficient on the left hand side is 3, on the right hand side is 6a minus 4b plus c. The a is 0, the b is 1. We can use that to find c. So c equals to positive 1. And then for the constant term, positive 7 on the left hand side is equals to 6b plus d. b equals to 1. So d also equals to 1. So then the integral, which is x squared minus 3x plus 7 over x squared minus 4x plus 6 being squared dx is now equals to 1 over x squared minus 4x plus 6 plus x plus 1 over x squared minus 4x plus 6 being squared dx. That is equal to integral. I will separate them. Okay, so this is dx over, and let me complete the square right away at the bottom. So I get x minus 2 squared plus 2 plus integral x plus 1 over x minus 2 squared plus 2 being squared dx.
Wouldn't you want to separate the +1 from the x?
Yes, that's what I have in mind. Okay, so this will be du over u squared plus 2 if u equals to x minus 2. So du is equals to dx, right? Okay, so this will be u minus 1 over, hold on, x plus 2. That's actually x, u plus 3, I'm sorry. That's u plus 3. Yeah, and then this will be u squared plus 2 being squared du. The first integral is okay. This is 1 over radical 2 tangent inverse of u over radical 2 plus the second one here. I don't know. Yeah, I guess I will separate them. Let me use w equals to u squared plus 2. So dw equals to 2u du. Okay, so now this stays the same, the first term. Plus the second term will be 1/2 integral dw over w squared, right? And then how about the last part?
Wouldn't you want to do the same thing for the last one?
I can, but I have issue with the du later on. So this will be w squared, right? Okay, but how about the du? So w minus 2 under square root equals to u. So 1 dw over 2 square root of w minus 2 equals to du, which is uglier.
Wait, why is that? I don't get it. Oh, okay, wait a minute.
I differentiate them.
Oh yeah, that's really ugly.
Which I don't think that's how I will do it. But it could be the only way, you know, that could be the only way. Well, anyway, let's leave it like that for now. You know what? Let me just leave it like that. I will think about this later. For now, I will just write it down without any modification. It seems like that is the only way to do it though. So I get this is radical 2 over 2 tangent inverse of u radical 2 over 2 plus actually becomes minus 1/2 1 over 2 w. Okay, plus now that one. How to integrate this? Yeah, it seems like I have no other way though. Seems like I need to use that 3 dw over 2w squared square root of w minus 2. Yeah, seems like I have to do it that way. Anyway, at least I localized the problem. At least I localized the problem. This is radical 2 over 2. I just keep on copying this. But then I change this w back. That's 1 over 2 times w. W is u squared plus 2, but u squared plus 2 equals to what? U squared plus 2 is x squared minus 4x plus 6. And then I will substitute this w back. Okay, so this is 3 over 2 integral. Yeah, I don't really like to do this though. How do we integrate this? You know what? You know what? Let's not doing this way.
Could you have separated x plus 1 early on without getting the 3?
But you
Yeah,
still
like up
need to,
there.
yeah, but you still need to get that x becomes u plus 2.
Oh.
Right? Okay, and that plus 2 will combine with the 1, give you that 3. But I guess that's not how I'm going to do it. I think I will do this way instead. U equals to radical 2 tangent theta. So du equals to radical 2 secant squared theta d theta. And the integral, which is like, this is 3 over u squared is 2 tangent squared plus 2 becomes 2 tangent squared plus 2, that's 2 secant squared. So the bottom will give us 4 secant to the 4th theta. Oh, yeah, this is the way. Now du becomes square root of 2 secant squared theta d theta. Right, get the bum, get the boom, 3/4 comes out. 3 radical 2 over 4 comes out. And the guy inside here basically just secant cosine square. You see the secant square cancel. You have secant square at the bottom. Right? Secant square cancels, right? But so you have secant square at the bottom, which is cosine on the top. Cosine square on the top. Okay, so this is 4, this is radical 2, and then cosine square is 1 plus cosine 2 theta over 2 d theta. Oh, wow, it's quite painful. Plus 3 radical 2 over 8 times theta plus 1/2 sine 2 theta plus constant. What is my u again? U is x minus 2, huh? Okay, so radical 2 over 2 tangent inverse of x minus 2. So x radical 2 minus 2 radical 2 over 2 minus 1 over 2x squared minus 8x plus 12. You don't need to distribute that 2 actually. And then 3 radical 2 over 8. What is my theta? So tangent theta is u over radical 2. So this is square root of u squared plus 2. In terms of x, this will be x squared minus 4x plus 6. This is x minus 2. So theta will be tangent inverse of, you know what, let me just leave this as u over radical 2. That's tangent inverse of u over radical 2 plus sine theta cosine theta. I want to combine like terms, this one here and this one here. Okay, multiply by 4, so I get 7 radical 2 over 8 tangent inverse of u, that's x minus 2 over radical 2 minus 1 over 2 times x squared minus 4x plus 6, and then plus 3 radical 2 over 8 sine theta, which is u over that, cosine theta is that. So it's radical 2 times u over radical u squared plus 2 plus constant. Ooh. Oh, you know what? Something actually gets nicer here. So this will be 6/3 3u over 4 square root of x squared minus 4x plus 6 plus constant. Okay. Trust me, you need to be very, very, very patient, huh? Just do it, you know, just do it. Just do it. Okay, time to check. Wish me luck. 7.4, number 39. Huh? Why my answer is so different? This is number 39, right? Oh, no, 37. The first term is correct. The second term is not correct. Oh, I think I know why. I need to change this u back. This u is what? X minus 2. Yeah, this is not correct. What I have here is not correct. This guy with this guy. Oh, my denominator, denominator. I should not have square root here. It's supposed to be square root being square. So no more square root there. Oh, then we go on. The first term is already okay. I check with the book. Yeah, I make mistake with that square root there. And then here I do LCD. So 2 over 4 times that ugly guy plus 3. Actually, it should be negative 2 here. So 3x minus 6 plus c. That's a long question, huh? But I did it just by intuition. I just keep on going, keep on going, keep on going. There could be a better way to do this though. Yeah, there could be a better way to do this problem.
I don't think I could have figured that one out.
Don't. If your comment actually is, if you could figure out in 5 minutes, definitely not. Definitely not.
Definitely not.
Right? Okay, but if I say if I give you 15 minutes to try it, and just think of it this way: like you need to go as far as possible.
Yeah.
Right?
I think I probably would have made it. I think I would have gotten stuck at the that last integral, the one that you had to use squared
trig substitution.
I mean,
yeah.
Yeah. I think that's where I would have messed up, even though it was looking familiar, and I kept thinking it had something to do with tangent. I just didn't know how to apply it.
So this question is good because it involves first partial fraction decomposition, completing the square, inverse tangent, right? Yeah, it's basically everywhere. No wonder it's difficult, right? It's like you need to know basically everything and when to use each one of those. It's not easy, but it's to say that it's not doable also not right. It's doable. It takes time, right?
Yeah, I think it's just practice, and like you said, it's intuition. Like especially if you've been studying.
Yeah, just keep on. What you need to have at these sections, to be more precise, at 7.5, is like your intuition of when to do what, and that you can only have that by doing a lot of problems and see people doing that. Okay. In other words, you see, I myself get so discouraged when I saw this. I mean, you can tell that of the whole procedure here, I get stuck here.
Yeah.
Right. And then I was actually like try to do substitution. It doesn't work. And then I realized, oh, you know what? The only way I can get rid of this guy nicely is by using trig substitution. But that will be ugly because of that square root of 2.
Right.
Right. Now the thing is like, is it a good reason for me not to do it at all? It turns out that's the only way.
Right? Right. Yeah, I know. I mean, I'm still trying to like give myself the benefit of the doubt, because I doubt myself so often, and then when I actually go through it, I'm like, oh my god, like I actually had it right, and I just went the longer way for no reason.
Think of it this way. What I'm about to say right now is actually is more than just the technique. It's about desperation. If you are desperate, do I spell it right?
I think so.
Not A here? A or E here?
No, that's E.
That's E? Okay.
It's an E. Yeah.
Okay. When you are desperate, you're basically being cornered in your life. What do you do? And committing suicide is not one of them.
Obviously.
So if you are desperate, what you do?
That's the easy way out. Living is hard.
Yeah. Yeah, look for solution. Now, the thing is like when you say you look for solution, and we don't have an easy solution. right? Life is hard because of that. We don't have easy solutions. Sometimes you need to work it out. And at the beginning, we usually have issue with like, which one will work out, right? So when you are desperate, just do something. And you know, if it doesn't work, if it doesn't work, we are no worse than earlier. Right? Because you already get stuck anyway. You see what I mean? Right? Doing nothing will not make it work at all. Okay, doing something may fail, but at least you do something and you are not in the position where you are getting worse. At least you try. Okay,
That's
and
true.
this is not like in real life where you do something, it may cost something and you lose something, right? This is at least just abstractly calculus, right? Okay, if you try a method, it doesn't work, at least you are stuck anyway at the beginning. So nothing to lose except some time. Right?
And your
Okay.
sanity a little bit.
Yeah, but it is possible that you learn something new in between. Then it doesn't work. If I do it this way, because of what? It works because of what? Now, of course, you don't want to be cornered in this situation when you take a test. So try to do it earlier in your practice. The more you practice, the more you prevent yourself to be desperate during the test. Now, I'm not saying this easily. I'm not saying this easily. I did a lot of problems, You can choose any, I told you, you can choose any problems from this book and ask me to do it. I may get stuck, but I will not say, you know what, I'm scared. No, I will just do it anyway. And I won't be embarrassed if I end up saying, you know what, I don't know what to do. Why? Because if you can find a question that I cannot do, that will be a question I will do in future. Right? Either I do it now or later, eventually, right? On the top of that, when I did my undergrad, I told you that we have three main textbooks. We have three textbooks and we have three supplemental textbooks. The way we practice, we basically practice most of those problems. So I get stuck. Put it this way, the number of times you get stuck in this class is still less than the number of times I get stuck when I did the problem in Calculus 2, when I took Calculus 2. Why? Because we did problems from 6 different textbooks. So the reason now I don't get stuck as much is because I have done my quote unquote work at that time. Okay. So don't feel bad to get stuck. It's fine. Okay, let me know where I can help you. Okay, and from there we can find mistakes.
Yeah, I just felt bad because I sent you so many.
No, that's okay. That's
But
okay.
I gave myself a second chance. Like I gave myself another day with fresh eyes and a fresh brain, basically. And
No.
I was able to figure some things out, but other ones I just said I can't. I don't know what to do.
No, that's okay. I just feel like if you can send me those questions not on Monday or Wednesday, that would be great. Send it to me on Saturday or Sunday, where I have more time. Because Monday, Wednesday, Monday, Wednesdays are my long days. I teach basically from 8:45 in the morning until 10 o'clock at night.
Oh wow, that really is a long
So
day.
this is my schedule on Monday, Wednesday, 8:45. That's my office hour at Santa Monica until 12 o'clock, and then 3 o'clock to 10 o'clock. So my break basically only 3 hours. But in these 3 hours, I usually still, like what I did to you, I answer questions. So I'm answering not only your question, I answer other people's questions also. Right? And then answer questions, of course, reply email, administration stuff, and so on and so forth. right? So, I mean, in other words, I only went over the problem you highlight earlier, and I didn't have a chance to go over problems you didn't highlight. But I know
Oh
you have
yeah,
questions.
yeah, the ones I didn't highlight, I figured those out. I was able to do them because it's funny because um once I figure one out, I realized, oh wait, this looks familiar, or this, I think I can use this same trick on that one, and that's how I was able to figure those out. And I
Mm,
mean, I got the answer in the back of the book, so
mm,
it checked out. So
mm.
I was just like, okay. So the ones I highlighted were the ones that I really needed help on.
Let's do it this way. You know the discussion board that we have? Let me go to our discussion board. I would like you to have this. The thing is, we cannot really meet, right? So I would like you to do this. Like, for example, the material that we went over last time on March the 15th. I think we did 7.4 and 7.5 and 7.8, maybe. I don't remember precisely, or maybe 7.4. With 7.5, 7.8. Now, like the problem that you did, you post it here. So that's from 7.5, 7.8, right? So if you already done some problem, you post it there, including the one that you get stuck. So not only me responding to you, you have other students looking at that also. What do you think?
Okay. Okay, yeah, we can do that. I can, if it's
So
okay with you, if I could do it on both, I could email you and put it on the
yeah,
discussion.
that's right. So even for problems you did okay, I assume that another students, let's say Shane or Robert, may post their own solutions also, happen to be on the same questions but different work, right? That
I
way
think that's a great idea.
that way we can learn from each other still.
Yeah,
Okay.
I think I think that's an actually great idea because maybe somebody else might do it a different way that might actually be easier than the way I'm doing it. Because clearly, I like it the long and hard way. So
Or it's in case you have question. The thing is, like, if you are someone who feel embarrassed to ask question, then you may take it against your pride, while actually it's totally
oh
fine
no,
to ask
Thomas,
question.
I have no problem asking questions. I mean, how are we ever gonna pass this class if we never ask questions?
That's true. And you help other students not to feel embarrassed also, because it's supposed to be just how to say it the right way. It's supposed to be just a common situation where we get stuck, you and me. I've been doing calculus for longer times. Of course, I get less stuck. Right. But when I was in your place, I basically the same thing could be even worse. Right. Okay. And getting stuck is not something to be embarrassed. It's something that we can learn from. Why I get stuck, what I have not really, what kind of intuition that I don't really master yet, so on and so forth. Okay.
Yeah, for sure. I
Now
think that's a great idea.
mhm, let's do it that way. Now, 7.8, let me continue. 7.8, we finished infinite integral last time, integral from something to infinity, from negative infinity to something. But I would like to go over some stuff that I think I didn't do last time, something called P integral. Something called P integral, extra stuff. No, I should not call this extra, but maybe I call that leftover then. Something I didn't finish last time, leftover. Yeah, calling that extra as if it's optional, you need to know or not. Oh, it's in my lecture. Oh, okay. So should I go over that? At least I mentioned it then. Okay. Integral of 1 over x to the p dp
We I don't think I
dx.
could. I don't think we can see your screen, Thomas.
Huh? What did I do?
I'm still I'm still seeing your canvas. Or
Oh,
weird.
thank you. Thank you. Thank you for reminding me. Yeah, I'm here. Okay, so integral of 1 over x to the p dx is convergent, divergent when p is less than equals to 1. It is convergent to when p is greater than 1. In fact, it is convergent to what? It is convergent to what? I don't remember that. I think that's 1 over 1 minus p. Oh, by the way, that's from 1 to infinity. Negative of 1 over 1 minus p. Is it right? Let's see. Let me check. I try not to look at the book. Okay, let me check. Integral of 1 over x to the p dx from 1 to infinity. That is for p greater than 1 is equal to limit t goes to infinity for integral 1 to t of x to the negative p dx. That's limit t goes to infinity of 1 over 1 minus p x to the 1 minus p from 1 to t. So that's limit t goes to infinity of t to the 1 minus p over 1 minus p minus, when x equals to 1, that's just 1 over 1 minus p. But this is the same to limit t goes to infinity of 1 over 1 minus p times t to the p minus 1. So this will be 0. Okay, basically, if the exponent less than or equals to 1, then this integral will go to infinity. Oh, you didn't see this one in the video? I think I went over this though. I believe I went over this. Maybe I just used different notation. Yeah, because of this though. If p is less than equals to, yeah, greater equals to 1, means p minus 1 is positive, 1 minus p is negative. No equal sign. Oh, I wrote it as 1 over p minus 1. Oh, okay, okay. Yeah, that makes sense. That makes sense to absorb the negative. So that's 1 over p minus 1. Thank you. Thank you. Yeah, that makes more sense. What am I doing? So that's 1 over p minus 1. Thank you. Okay, to absorb the negative. Now, even though it is from 1 to infinity, it actually works the same way even if you don't have 1 here. Okay, let's change it to another number greater than 1. So for a greater than 1, then integral from a to infinity of x to the 1 over x to the p dx. All we need to know is actually its divergent when p is less than equals to 1 is convergent. This is my notation for divergent convergent when p is greater than 1. Okay, think of it this way. Think of it this way. If the integral from 1 to infinity is finite, then if you start from a, it is still finite, right? Because you actually subtract by some finite area here. Now, on the other hand, On the other hand, if the integral from 1 to infinity already infinite divergent, then the reason it is divergent is not because this finite area, it must be because of this infinite area here. So even if you start from some number greater than 1, it will still be infinite. Infinity, okay? Now that's actually get into convergence theorem though, comparison test, comparison theorem. Okay, but let me go on to part B. That's the integral involving singularity, discontinuous integral. Idea. Discontinuous integral. Suppose we have a function that is going to infinity at b. It goes to infinity at b. The way we will approach this problem is we will integrate up to t first and push this t approaching b from left-hand side. If the singularity is actually on the left-hand side of the integral, let's say from b to c, right? Singularity at b, then we will integrate from, let me call this s then, from s to c, and then you push this s to b from the right-hand side. That's the idea, okay? That's the idea. Now, I don't want to spend too much time there with the theory. We apply that with examples right away. Number 28. If you want to look at the theory, take a look on the videos. Okay, number 28, integral from 2 to 3 of 1 over square root of 3 minus x dx. Notice that when x equals to 3, I get 0 on the denominator. Right? When x equals to 3, I get 0 on the denominator. It becomes undefined. So you see that we actually having this case here. It's undefined when the x equals to the right end of that integral. So what I will do is I will change that 3 into t goes to 3 from the left-hand side. Okay, so you take a t which is less than 3, okay, and then you approach that t to 3 from below. Okay, integral 2 to t dx over square root of 3 minus x. Then we integrate that as usual. Okay, substitution u equals to 3 minus x, so du is negative dx, right? U at 2 will be 3 minus 2, that's 1. U at t will be 3 minus t. So the integral, let me continue here, will be limit t goes to 3 from the left-hand side of integral 1 to 3 minus t negative du over square root of u. So limit t goes to 3 from the left-hand side. I will absorb the negative by reversing order of integration. This is u to the negative 1/2 du. Now, what is the integral of this? That's 2u to the power of 1/2 from 3 minus t to 1. Is it right? That's a minus, not plus. That is 2 times, when u equals to 1, that's u. When u equals to 3 minus t, that will be 2 times 2. Limit t goes to 3 from left-hand side of 3 minus t to the power of 1/2. But that's 0. That's for number 28. So you see, I want to emphasize that what we learn in this section is only this part. That's the only thing we learn in this section. The rest, we already learned that before. Nothing new, nothing new. The only new one is the one I highlight in blue there. Okay, basically, if you deal with infinity, that's a monster, then you don't deal with them heads on. Okay, use limit. Okay, use limit. That's number 28, number 32. Number 32, integral from 0 to 1 of dx over square root of 1 minus x squared. Again, we have singularity at 1, right? When x equals to 1, we get something over 0. So I will change that to limit t going to 1 from left-hand side, integral from 0 to t dx over square root of 1 minus x squared. Can anybody help me with this integral super fast? What is the integral of dx over square root of 1 minus x squared? Almost right. Sine, almost right. Sine inverse. Okay. So this is limit t goes to 1 from left-hand side of sine inverse of t minus sine inverse 0, which is 0. And what is sine inverse of 1? Pi over 2. Right? See, if you don't memorize that, then you will spend a long time. Yeah, you substitute x equals to sine x, sine theta, and blah, 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 right? Okay. Yeah, that was easy. If you memorize that, if you don't memorize that, it will take you forever. So you will be dealing with limit and then inverse, inverse trig functions or trig substitution stuff later on. Number 38. I think number 38 is the hard one. Number 38. Integral from 0 to 1 of e to the 1 over x cubed dx. Now singularity at 0, right? That's limit t goes to 0 from the right-hand side, integral t to 1 e to the 1 over x cubed dx. Ooh, I think I will do substitution here. I don't like that e to the 1 over x. So let u equals to 1 over x. So du will be negative 1 over x squared dx. Let's see. I think I need to rewrite that first. So limit t goes to 0 from the right-hand side, integral from t to 1, e to the 1 over x over x squared dx. That's limit t goes to infinity, 0 positive. This becomes 1. This becomes 1 over t e to the u over, that's u, huh? And negative du. Okay, so this guy here is this. That's negative du, right? This is 1 over u. I mean, this is u. Okay, and this is also u. Okay, then this is equal to limit t goes to 0 from positive side of 1 to 1 over t. I sort the negative by reversing order of integration, u e to the u du, integration by parts, 1, 0, e to the u, e to the u. So this is equal to limit t goes to 0 from the right hand side of u e to the u minus e to the u from 1 to 1 over t. Limit t goes to 0 positive of 1 over t e to the 1 over t minus e to the 1 over t. When u equals to 1, that's e minus e, that's 0. Oh, so my issue is now here. Why did I get 1 over t? When I replace the u. When I replace the u, is it okay? Earlier, how did I get 1 over t from my substitution here? So u1 will be 1 over 1, that's 1, and ut will be 1 over t, right? Okay, now, oh, that's okay. I didn't write it down, you know. Yeah, remember, every time I do substitution, then I need to change the limit right away, okay? The limit now is in terms of u. Let's come back here. This guy is 0, so that's fine, but we have issue with this because if I plug in t goes to 0 on the positives from the right hand side, I get what is this? Infinity times 0 minus 0. Oh no, it's something with infinity. I get infinity over infinity. Well, let me rewrite this. This is e to the 1 over t times 1 over t minus 1. Do you see that? So this is, yeah, it seems like we need to massage this and play with L'Hopital rule later on. This is e to the 1 over t times 1 minus t over t. I will do L'Hopital rule. So this is e to the 1 over t times negative 1 over t squared times 1 minus t plus e to the 1 over t times negative 1 over 1. I wonder if it makes it a lot better in any way. I do product rule on the top. Why isn't it infinity times infinity? The thing is, what we have here is infinity, or infinity times 1, but this is 0. Oh, that would be infinity, huh? Let me check. Am I doing this too early? Now, the way I see is this, at least from here, I cannot do that. I cannot do that here because this is infinity minus infinity, right? Okay, and then I wonder if I rewrite this correctly. I factor e to the t, e to the 1 over t, so I get this, right? That's 1 over 0, that's infinity over infinity, huh? So, yeah, the step in between the highlights. Yeah, maybe I don't need to use L'Hopital rule, huh? But let's take a look first. Let me slow down then. I rush into L'Hopital rule. How to say that? This will be 0 from positive side. This will be 1, and this will be positive infinity. It's infinity to the infinity thingy, huh? Anyway, I think I can just stop here and then call this infinity. Because I get on the top, I get e to the 1 over 0 positive. That's e to the infinity, 1 minus 0 over 0 positive. So this is infinity over 0 positive. That's positive infinity. Now, what I write in red here is actually not correct notation. That's why I write it in red. That's something you do on your scratch paper. But you need to make sure that when you replace t by 0 positive, you get that though. You know what? My life will be a lot easier if I do this. This is equal to limit u goes to infinity of u e to the u minus e to the u. Right? I basically replace the t becomes 1 over t, but if t goes to 0, then 1 over t goes to infinity. Right? So this is limit t, u goes to infinity of e to the u minus 1. Then it becomes clear that it is infinity. This is infinity times infinity. I think that's a better route. Okay, I choose a problem that I myself don't know how to answer precisely. Yeah, again, I just let it flow. Okay, I just let it flow. I think the last question I would like to do from this 7.8b is number 40. And then we go to comparison theorem. Number 40, integral from 0 to 1, natural log of x over square root of x dx. Again, it is singularity at 0. Singularity at 0. How do we do this? Any idea? Let's write it this way. This is integral, I'm sorry, limit first. That's limit t goes to 0 from the positive side of integral t to 1. Natural log I will differentiate and I will integrate 1 over radical x dx. Okay, hopefully we get something nice. So this will be 1 over x. The integral of that will be 2x, 2 square root of x dx. Right? Okay, so this is equals to limit t goes to 0 from positive side of 2 radical x natural log of x from t to 1 minus integral 2 times square root of x over x dx from t to 1. This is integral from t to 1 of 1 over square root of x dx again. Oh, but we know what's that. This is an x, not a 2. This will be 4 square root of x from t to 1. Now plug in numbers. So 2 radical 1 ln 1 minus 2 radical t limit t goes to 0 positive 2 ln 1 minus 2 radical t ln t. Ooh, wow, that's ugly. Minus 4 minus 4 radical t. This is 0. This is 2 natural log of t over over 1 over square root of x minus give me a second. The first term is 0 minus net limit t goes to 0 positive of 2 ln t over 1 over square root of t, and then minus 4 minus 0. So that's negative number. something minus 4. But I don't know what is this. What do you think we should do from here? The reason I do it that way because we do L'Hopital rule, right? Okay, so that's -4 minus limit t goes to 0 positive. On the top, I will get 2 over t. At the bottom, what do I get? Okay. So this will be -4 minus limit t goes to 0 positive. We have negative, bring it to the front. We get 4 on the top, t to the 3/2 over t. That's 0. Oh, I didn't expect that though. Okay. Yeah, that's for number 40. The last part of this section, 7.8 part C, is on comparison theorem. Comparison theorem. Suppose we deal with positive integrand, let 0 less than equals to gx less than equals to fx, which means on the coordinate system, let's say this is A here. Okay, now then the graph of fx is always positive above the graph of gx. Okay, so this is our gx and this is our fx. Now the idea is the following. The idea is following. If the area under f, which is greater, if the area under f is finite, then the area under G must be even smaller, right? Does it make sense? Okay, so if integral from a to infinity of fx dx is convergent, where the fx is greater, then the integral, or basically the area for any function less than fx, in this case gx, must also be finite. Okay, if the yellow one is finite, the area of the yellow region is finite, then the area of the blue region must also be finite. Now, on the other hand, if the area of the blue region is divergent, if it goes to infinity, it won't go to negative infinity, by the way. It'll be positive. If it divergent, then it must go to positive infinity, right? Because the area is positive, the function is positive. Okay, now if gx, which is the smaller function, already have infinite area under the curve, then the area of the function above that, any function above that, must be also divergent. Okay, now, so the challenge here is to bound it above, to bound it below. Number 50, which I think I did in my lecture. Anybody watch the lecture yet? Did I do number 50, 52, 54? Or did I do number 49, 51, 53? Did I do even number or odd number? Oh, I did even number. Okay, let me do odd numbers right now then instead. Okay, so number 51, 49, number 49. This type of question, comparison theorem, actually being used a lot, even if you go up to graduate study. Okay, basically, before we know what is the integral, before we know to find out what's the integral, we want to first find out if it is convergent. Okay, this is integral from 0 to infinity of x over x cubed plus 1. X cubed plus 1 dx. How do I do this? Keep in mind that our purpose is not to find what is this integral. It's just to find out if this integral is convergent or divergent. Okay, so maybe I write it properly. Is this integral convergent or divergent? Okay, that's all we want. And solution, if you think it is convergent, then you try to bound it above by a bigger function that is convergent. If you think it's divergent, then bound it below by a function that is divergent. Now, the reason I asked you to memorize that P integral is the following. Integral from 1 to infinity of 1 over x to the P dx is convergent when P is greater than 1, right? Okay, now you see that the degree on the top and the bottom differ by 2. Okay, so what I want to say is at large x, when x very large, the behavior of x over x cubed plus 1 will be very similar to 1 over x squared at large x. Okay, now the thing is, do you realize that this is equals to, let me separate this integral from 0 to 1 of x over x cubed plus 1 dx plus integral from 0 to 1 of x of, from 1 to infinity x cubed plus 1 dx. What I want to say is that it has nothing to do with the 0. It's not about this 0. It's not about this 0. Okay, it's not about that 0. And notice that in from 0 to 1, between 0 to 1, notice that x over x cubed plus 1 is less than equals to 1. At most it is 1. Is it right? How do you know that, Thomas? On that intervals from 0 to 1, notice that That's the claim proof. Because x is less than equals to x cubed plus 1. Right? When x between 0 to 1, maybe I put it this way then instead. I really want you to see it. Notice that between 0 to 1, x is less than equals to 1. Agree? If I add a positive number, then x still less than 1 plus x cubed. Is it right? Therefore, x over 1 plus x cubed will be less than equals to 1. So in this interval, I can bound this above by 1. Thomas, how do you know that you need to do that? I just want to bound it. I just find some way to bound it. But Thomas, why 1? Why don't you use 2? You can. If you want to use 2 here instead of 1, go ahead. But you still need to show that why it's true though. Okay. Now, another thing, how about the right-hand side? Notice that on the right-hand side here, in the interval 1 to infinity, notice that x cubed must be less than equals to x cubed plus 1. Is it right? Must be less than. Therefore, 1 over x cubed must be greater equals to 1 over x cubed plus 1. If you have a positive number, okay, both of them positive. If you take the reciprocal, then the order reverse. Like 2 is less than 3. When you do reciprocal, then 1/2 is greater than 1/3. You see what I mean? You divide by a larger number, the result is smaller. The quotient is smaller. Okay, now multiply by x on the top, and x is positive, right? So what we have is integral from 1 to infinity of x over x cubed plus 1 dx is less than equals to integral from 1 to infinity of x over x cubed dx, which is equal to integral from 1 to infinity of 1 over x squared dx. So I bound it above by integral from 1 to infinity of 1 over x squared dx. Okay, now then you quote by p integral, that's why you need to memorize that. By p integral from 1 to infinity of 1 over x squared dx is convergent. And can you tell what is integral from 0 to 1 of 1 dx? What is that? All you need is actually that's convergent. Okay, all you need is a convergent. So because it's bounded by something convergent, then integral from 0 to infinity of x over x cubed plus 1 dx is convergent. Now notice that I did not try to compute I did not try to compute what is that. Okay, I did not try to compute. I just want to see if it is convergent or not. In fact, we can say here, note that from the formula we have integral from 1 to infinity of 1 over x squared dx is convergent to 1 over 2 minus 1. So we can say this is equals to 1 plus 1, which is 2. Okay, so this guy is less than equals to 2. So this integral is convergent, bounded above by something finite. It is convergent. Okay, let me emphasize. It's not about these two. No, you don't need this. You don't need this. You just need that to be convergent. Okay, let me mark it in blue instead. You just need that to be convergent. So if that integral, you notice that we start with this, right? This integral is exactly equals to this, and that integral is less than this. Less than. And we know the right-hand side here is finite. Right? Is finite. So this must be finite. Okay. Now it will not be negative because we know the integrand is non-negative, right? The integrand is non-negative. So the area under the curve here must be positive, yet it is not infinity. Yet it is not infinity. So the only way is it is finite. I'm sorry. Let me play the movie again. Integral from 0 to 1 of that function. Okay, not 0 to 1, 0 to infinity. I break it up into integral from 0 to 1 of fx plus integral from 1 to infinity fx dx. Thomas, why do you break it up that way? Because of the following. I want this to follow my p integral. It's not precisely p integral, but it is bounded above by a p integral with p greater than 1. Now, this guy here, I bound it above by integral of 1. And it doesn't have to be 1. You can just make it 2 or 3. Basically, you bound it by something finite on a finite domain. Finite function on a finite domain must be finite area, right? Now, the challenge is this is infinite domain, but it's p integral, so it's finite. Now, that's what you want. So if both integrals are finite, then the sum must also be finite, right? So this function is convergent. Okay, that's my scratch work. That's my scratch work. So for this part here, let's say that you really need to have some plan on how to work around. Let me do one more problem and then I give myself a break. Number 51. Integral from 1 to infinity of x plus 1 over square root of x to the fourth minus x dx. Let's take a look on, it's already start from 1 to infinity though. So let's take a look on this guy here, x plus 1 over square root of x to the fourth minus x. This must be greater than x plus 1 over square root of x to the fourth. Is it right? Why? Because if you subtract by a positive number, then it becomes smaller. If you divide by something smaller, the quotient is bigger, right? And I can do even more. This is x squared, right? Okay, on the top, x plus 1 is greater than x. So let's see how I play with this. So this is integral from 1 to infinity of x plus 1 over square root of x to the fourth minus x. I'm sorry, I get rid of the minus x dx, right? This is actually greater than, that's greater equals to integral from 1 to infinity of x over x squared. I compare x plus 1 with x plus 1 is greater, while x square root of x to the fourth is the same to x squared. But this is equal to integral from 1 to infinity of 1 over x dx, which is divergent. So because it's bounded below by a divergent integral, so integral 1 to infinity of x plus 1 over square root of x to the fourth minus x dx is divergent. Lastly, let me give myself a break. We come back at what time? 10 minutes from now? 9:05. We come back at 9:05. I'm sorry. Let's continue with number 53. Integral from 0 to 1 of secant squared x over square root of over x square root of x. The denominator seems to follow. Well, I think I need to come up with something. Is this something we can bound above? Okay. I try to bound it above by some constant over x square root of x, because that will be constant over x to the power of 3/2. And then I can use p integral. The p is 3/2, which is greater than 1. So we look back, secant square of x can be bounded above by what number k in that on that interval 0 to 1. Now we know that secant graph of cosine is like this, right? This is pi over 2. Okay, so 0 to 1 will be approximately from here to somewhere here. But that's for cosine. Secant, however, will be something looks like this, right? In other words, I can use secant 1 as the upper bound of that. Secant squared 1 over x square root of x. Okay, so this is upper bound of bounded above by integral. Why I cannot? From 0 to 1 of secant squared 1 over x square root of x dx. That's equals to secant squared 1 integral from 0 to 1 of, oops, hold on. Hold on, I cannot use p integral. I'm sorry, I cannot use p integral. I cannot use p integral. My bad, my bad. Why? Because this is not from 1 to infinity. This is from 0 to 1. Before I start, you know what? I apologize. I apologize. Let me figure out first. How do I want to bound it? By first, no, this is not p integral. My bad. This is not p integral. This is not p integral. Erase, 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 erase. I forgot that's from 0 to 1. That's from 0 to 1. That's not from 1 to infinity. It's from 0 to 1. Let's integrate this first. So let me do it aside. Integral from 0 to 1 of 1 over x to the power of 3 half dx. Will this be convergent or divergent? We don't know. I don't know. I don't know. It's singularity at 0. So limit t goes to 0 from the positive side of integral t to 1 over x to the power of 3 half dx. I think this will go to explode to infinity. That's why. So this is integral from t to 1 of x to the power of 3 half dx. That's limit t goes to 0 positive of negative 2 x to the power of negative 1 half from t to 1. That's negative 2 plus 2 over square root of t. I forgot the limit. Yeah, this will be infinity. This is divergent. So I need to bound it below instead. I need to bound it below instead. So I will bound it below by secant squared 0. But secant squared 0 is 1. Then I basically do whatever I have here. The thing is, this is bounded below by secant squared 0 over x square root of x. So that integral from 0 to 1 of secant squared x over x square root of x dx is divergent. Now, so far we deal with a case where it's convergent only on only type 1 or type 2. Number 56, when we have both types. Number 56, integral from 2 to infinity of dx over x square root of x squared minus 4. So if we take a look on the number line, it starts from 2 to infinity, right? Now the thing is we have singularity at 2. When x equals to 2, it is singularity. Cosine inverse, I don't think there's cosine inverse. I think this is secant inverse instead. Yeah. Well, anyway, we have singularity at 2. We also have going to infinity, right? So I need to break this integral up into 2 parts. Just choose a random number in between. Let's say 3 or 4 or 5 or 10. That's okay. Yeah, I use 3. Okay, so I will break it into integral from 2 to 3 plus integral from 3 to infinity. You see how I break it up? Now then, if you happen to memorize, that's great. If you not, then we need to do it long way. Okay, limit t goes to 2 from the right-hand side of integral t to 3 dx over x square root of x squared minus 4 plus limit s goes to infinity. You cannot use t anymore because you already used t earlier. T to s dx over x square root of x squared minus 4. Honestly, I don't remember what is the integral of 1 over x square root of x squared minus 4. I will do substitution. Okay, so x equals 2 secant theta. So dx equals to 2 secant theta tangent theta d theta, and it applies to both of them. Two secant theta tangent theta d theta over my x is 2 secant theta. My square root of x squared minus 4, that's 2 tangent. That's 2 tangent theta. Oh, they cancel very well. I get a message coming in. Let me see. Yeah, it's secant inverse. But suppose I don't remember it's secant inverse, then I have to do it long way. Okay, so this is limit t goes to 2 from the right-hand side, integral from t to 3 of d theta plus limit, or actually 1/2 d theta, limit s goes to infinity of integral 3 to s of 1/2 d theta. Okay, so this is 1/2 theta, but my theta is secant inverse of x over 2 from t to 3. Don't forget the limit t goes to 2 from the right-hand side plus limit s goes to infinity of 1/2 secant inverse of x over 2 from, I make a mistake up there actually. I make a mistake up there actually. But let me go back to fix it. So this will be from 3 to S. Can you find out my mistake? In the last 2 lines before the last line. So the first term and the last term cancel. So I have limit s going to infinity of 1/2 secant inverse of s over 2 minus 1/2 secant inverse of 1. 2 tangent. No, the 2 tangent is correct. The 2 tangent is correct. My mistake is actually here. These are my mistake. Those are my mistake. Because I did substitution, right? Right. So the t cannot be t anymore. It should be secant inverse, like this one here. It's supposed to be secant inverse of t over 2. This is secant inverse of 3 over 2. That's what it's supposed to look like. Secant inverse of s over 2 is secant inverse of 3 over 2. Okay, so likewise for this, let me just cross it out so that you know you need to fix it. Okay, so it's supposed to be, let me correct that from here. So it's supposed to be theta from secant inverse of t over 3, t over 2 to secant inverse of 3 over 2. And the one here supposed to be theta, 1/2 theta from secant inverse of 3/2 to secant inverse of s/2. But what is secant inverse of infinity? When will secant be infinity? At pi over 2, right? So this is 1/2 times pi over 2 minus 1/2 times secant 1 is 0. So the answer is pi over 4. Wow, that's a long one, huh? Yeah, the question here is evaluate, so I need to get the result. Let me go on further. Which other question I want to do? Number 56. Page 555, number 42. page 555, number 42. Integral from 1 to infinity of natural log of x over x to the fourth dx. The question is evaluate or show that it is divergent. Is it convergent or divergent? And if it is convergent, find out what's that. So this is equal to limit t goes to infinity, integral from 1 to t, natural log of x over x to the fourth dx. Now what? This is limit t goes to infinity over natural log of x times x to the negative 4 dx, integration by parts, that's 1 over x. This is negative 1/3 x to the negative 3. Okay, so that is equal to limit t goes to infinity of negative 1/3 x to the negative 3 natural log of x from 1 to t minus becomes plus integral 1 to t of 1 over x times 1/3 x to the negative 3 dx. So this is negative natural log of x on the top over 3x cubed from 1 to t plus 1/3 integral from 1 to t of x to the negative 4 dx. In the integral, yeah, but I have negative here, but that's a negative also here, supposed to be. So it's supposed to look like this. Okay, subtract by the integral of the negative. Okay. Now then, that's limit t goes to infinity of negative natural log of t over 3t cubed plus natural log of 1 over 3 times 1 cubed plus 1/3 times negative 1/3 x to the negative 3 from 1 to t. Negative limit, it should be minus here. You know what? Let me do it this way. So limit t goes to infinity, negative natural log of t over 3t cubed plus 0 minus 1/9 limit t goes to infinity of 1 over t cubed minus 1. Okay, I will apply L'Hopital rule for the first term. Limit t goes to infinity of negative 1 over t over 9t squared plus, this is negative 1, right? So that's plus 1/9. when t goes to infinity here, this is limit t goes to infinity of -1/9t cubed. Oh, that will be 0. So that's 0 plus 1/9. That's 1/9. Number 46. I want to go over more questions because there are some type of question you don't see in that 7.8, but we need to address that. For example, number 46, integral from 0 to 1 of 1/2 minus 3x dx. Notice that the singularity is actually in between. The boundaries are 0 and 1, but the singularities happens at 2/3. Do you see that? Okay, the singularities happens at 2/3. Now let's do this one. So I will break it up there. Integral from 0 to 2/3 of 1/2 minus 3x dx plus integral from 2/3 to 1 of 1/2 minus 3x dx. Okay, now then apply the limit, but again, make sure that you don't use the same variable for the limit. This is to 2/3 from the left-hand side, integral from 0 to t of dx over 2 minus 3x plus limit s going to 2/3 from the right-hand side, integral from s to 1 dx over 2 minus 3x. Okay, so this is limit t goes to 2/3 from approach from left-hand side, and the integral of that will be -1/3 natural log of 2 minus 3x from 0 to t plus limit s going to 2/3 from the right-hand side. That's -1/3 natural log of 2 minus 3x from s to 1. I believe I taught you this before. 1 over integral of 1 over x dx. This is, we know this is absolute of, natural log of absolute of x plus constant, right? Now what happened if I have 1 over ax plus b instead? I replace that x by a linear multiple. Then there will be 1 over a natural log of ax plus b plus constant. Okay, so what I did there is actually that. Now the thing is, this is -1/3 limit t goes to 2/3 negative of natural log of 2 minus 3t plus 1/3 natural log when x equals to 0, that's 2 plus becomes minus 1/3 natural log when x equals to 1, that's 1 plus 1/3 limit s going to 2/3 from the right hand side of 2 minus 3s. Now the thing is, you will see that one of the integral actually goes to infinity. Once one of them, like this one here, goes to infinity, or actually both of them, one of them goes to infinity, the other one goes to -infinity. So what happened here is that this is divergent. This is divergent. right? So the whole thing is divergent. Okay, this part here is also divergent, but this go divergent to negative infinity. No, that one divergent to positive infinity. This one divergent to negative infinity. Okay, notice that when S goes to 2/3 from the positive side, then 3S approaching 2 from the right-hand side. Okay, so 2 minus 3S will be approaching 0 from the absolute sign here, approaching 0 from the positive side. Now then, what happened to the limit? That's approaching, need the, not limit, the natural log. Natural log here, so this will be natural log 0 positive, but this is actually going to negative infinity, right? I hope that explains what happened here. So basically, if you take a look on the graph, on that graph, I'm trying to explain to you what actually happened in between. So we have singularity at 2/3. Now the graph of the function looks like this. Looks like that. Okay, so the integral from 0 to something and the integral from something to 1, right? No, this is actually opposite. It's 2 minus 3x, my bad. It's the other way around. So it looks like this. That's what it looks like. Okay, so the integral from 0 to t, that will be up exploding to infinity, while the integral from s to 1, this is our 2/3 here. Okay, this integral here goes to infinity up to t. While the integral here goes to negative infinity. Now, once you have any part of the integral divergent, then the whole integral is divergent. Okay, you cannot say, oh, one of them goes to infinity, the other one goes to negative infinity, so they cancel each other. No, it doesn't work that way. Okay, it doesn't work that way. This question is not easy though. This question is not easy. You need to imagine, oh, you know what? We have singularity somewhere in between. You break it up into 2 integrals with 2 limits. Okay, and then when you observe, and once you have any part of that goes to divergent, then you have to stop and say the whole thing is divergent. Let me see, what's the last question I want to go over? Number 48. How do I know it's 2/3? The denominator, 2 minus 3x. 2 minus 3x equals to 0 implies x is 2/3. Is it okay? Okay, the last question from this I want to do is something not right with my computer again. Okay, number 48. Integral from -1 to 1 of dx over x squared minus 2x. You see, let's see, when will this be, when will this have singularity? So when x squared minus 2x equals to 0. So when x equals to 0 or when x equals to 2. Okay, but in this interval, -1 to 1, only 0 is there. Right, so I will break it up at 0. Integral -1 to 0 of dx over x squared minus 2x plus integral from 0 to 1 of dx over x squared minus 2x. Oh shoot, I need to do integration by parts later on, huh? Let me do the limit first. This is equals to limit t goes to 0 from the left-hand side, integral -1 to t dx over x times x minus 2 plus limit s going to 0 from the right-hand side, integral from s to 1 dx over x times x minus 2. Now, I wonder if you remember that. What is the integral? Anybody can help me note. This worth memorizing. What is the integral of 1 over x minus a, x minus b? Anybody remember?
Isn't it 1 over a minus b ln x minus a minus ln x minus b plus c, right?
Mhm.
Yeah.
Okay, so the way I see is, then this will be limit t goes to 0 from the left-hand side of, this will be 1/2 natural log of x minus 2 over x from -1 to t plus limit s goes to 0 positive of 1 over 2 natural log of x minus 2 over x from s to 1. So this is limit t goes to 0 from the left-hand side of 1/2 natural log of -2 over t minus 2 over t minus 1/2 natural log -3 over -1 plus of -1 minus 1/2 limit s goes to 0 positive of s minus 2 over s. But the thing is, oh, hold on. When t goes to 0, that will be something over 0, huh? Is it right? This is not going to infinity though. So what happened here is it's already going to infinity. That's divergent. Right? And this one is also divergent. You see? Okay, so this integral from -1 to 1 of dx over x squared minus 2x is divergent. Why I pick questions that is divergent all the time? Okay. Well, anyway, those are the hard questions that I want to go over from this chapter 7 review. With the time I have left, I have only around 7 minutes for 8.1. Let me just do it. 8.1, I believe my lecture is actually quite good already. So just watch that one. Okay, I give you the key idea. Okay, arc length. If I have a function and I want to find the length from A to B, the length of the function from A to B the length of the curve. Is given by integral from A to B square root of 1 plus dy dx being squared dx. Okay, if your integral is along x-axis from A to B. Now you can also do the integral this way. Let me use red color. Let's say this is from I don't want to use C for curve. This is from D to E. Okay, now that's equals to integral from D to E square root of 1 plus dx dy. The derivative of x respect to y instead, dy. That's the key. Now the thing is, I need you to practice on those though. Okay, I need you to practice on those. I believe I gave the suggested homework already for this 8.1. Please do those. Now, another suggestion is try to set up this guy here, the integrand. Try to set the integrand before you start the integration. Okay, that's my suggestion for you. Okay, let's say for example, I pick a question, question number 12. Okay, find the exact length of curve. Find the length of curve y equals to natural log of cosine x for x between 0 to pi over 3. And how will I do that? I will do the derivative first. Okay, notice that y equals to natural log of that. So dy dx, or basically y prime, is negative sine x over cosine x, right? Or which is negative tangent x. Now then, dy dx being squared will be tangent squared x plus 1 both sides. That gives us secant squared x. You see that? Okay, now the square root of this, we need to be a bit careful though. The square root of this supposed to be plus minus, supposed to be absolute of secant x. Okay, now, but in that interval 0.pi/3, secant is positive anyway. So you can just rewrite that as secant x. Now then the arc length will be integral from 0 to pi/3 of secant x dx. See, a lot easier, right? You don't want to deal with those administration inside the integral. You do it outside. Once it is simple, then you put it as your integrand. And from here, what is the integral of secant again? Natural log of secant x tangent x plus tangent x, right? From 0 to pi/3. So this is natural log of secant pi/3 plus tangent pi/3 minus natural log of secant 0, that's 1, plus tangent 0, that's 0. This is all integration, so should be Mickey Mouse for you. This is 2 plus radical 3 minus natural log of 1, which is 0. So this is natural log of 2 plus radical 3. That's the length. Okay, you will see situations where if you try to do all of them at once inside the integral, it will be quite painful. I think, for example, how about number 16? I have 0 minutes. I just take my time. Number 16, y equals to square root of x minus x squared plus sine inverse of x. They don't tell us the domain, but we can find the domain ourselves. Notice that the domain actually found here, right? Okay, so x minus x squared has to be at least 0. Are you with me? So step 1, critical numbers. X minus x squared equals to 0. X times 1 minus x equals to 0. That's x equals to 0. X equals to 1. Step 2, I do the sign graph. When x is greater than 1, that's negative. This is positive. This is negative. So the domain of this function, is from 0 to 1. Greater than 0. Inside the radical, it has to be at least 0. Right? It has to be at least 0. Now, so our integral later on, just a little preview, our integral later on will be from 0 to 1. Okay? Now then, let's see, that's how we get the domain of integration. How about the integrand of integration? Y prime equals to 1/2 times x minus x squared to the power of negative 1/2 times 1 minus 2x plus the derivative of sine inverse x is 1 over square root of 1 minus x squared. This is 1/2 times 1 minus 2x. At the bottom, I have square root of x minus x squared. And then plus 1 over square root of 1 minus x squared. Dude, this is fugly. I need to square this. Ah, man. Yeah, it's fugly. So if I square that, I just hope I don't make any mistake here though. Sine inverse x, the derivative is correct, right? Yeah, derivative of sine inverse x is 1 over that. Now, if I square that, it will be 1 minus 2x being squared over 4 times x minus x squared plus 2 times 1 minus 2x over 2 times square root of x minus x squared, square root of 1 minus x squared, plus 1 over 1 minus x squared. Man. And then I need to add 1 to that. Ooh. Do I really want to go on? I'm not writing the question incorrectly though. You know what? Let me ask you to continue on this. It's the class already end, but please continue. Please continue. Okay, and let me see what you get. I didn't expect it to. Oh, you know what? I make a mistake. It's square root of x here. Ah, I copied the question wrong. It's square root of x here. Sine inverse of square root of x. That helps. Okay, so the derivative will be, this is squared, right, times 1 over square root of x with 2. Now that helps. Okay, so this becomes I'm sorry. I know it's not supposed to be that ugly. At least I found my mistake. So this is 2 square root of x minus x squared. Yabby! They actually becomes really nice. Actually, I can cancel the 2, right? Okay, so it becomes 1 minus x over square root of x minus x squared. So if I square it, it becomes 1 minus 2x plus x squared over x minus x squared. So if I add 1, I'm about to stop, but I don't stop. What happened with me? I get excited. That gives me 1 minus x over x minus x squared. Oh, they cancel. That's just 1 over x. Dang it. So nice. So the arc length will be integral from 0 to 1 of 1 over square root of x dx. Oh, we have limit there. No, nice. Because this is square root, right? Okay, so we have limit here. Okay, so on and so forth. But basically it. I'm sorry. Okay, I will stop here.